So Redi is going to tell us about the no-cloning theorem in categorical quantum mechanics. Okay, please take it away.
Okay, so today, no-cloning theorem in categorical quantum mechanics. So yeah, I found the subject pretty interesting. Uh, Although we had a really busy week, I wish I had studied it in more detail. But anyway, I found the modeling part of this whole thing, because cloning is this concept from quantum theory, which means like cloning data, right? And it relates to, yeah. Anyway, so let me just. So I would like to break a little bit from the actual order of things in Vicary Heunen, because I think there are some important things that need to be mentioned. So I want to put this first in the context of general category theory. So let's recall a bunch of stuff from algebra. So a monoid, M, so this is one of the structures you learn in algebra. So a monoid M consists of a set M, and so a binary operation M cross M to M. So this is the multiplication. So we think of this map as taking a pair xy, mapping it to the multiplication, right? A monoid is somewhere where we can multiply things. I mean, we've been talking about monoidal categories, right? We are already ahead in this sense, but I just wanted to point out, so an identity element, which we think of as a map from the one-point set M, which send the unique element of the one-point set to something we call 1, okay? Which satisfy. So the first thing is associativity. So this means x times y times z is equal to x times y times z for all x, y, z in M, and we have unitality. Which means 1 times x is x, and x times 1, sorry, x times 1 is also x for all x in x. Okay, so this is a pretty simple concept. First thing you learn in algebra. So I wanted to point out that there is a dual notion. So by duality, we have the notion of a comonoid. So let's see how good our category theory is. So now you just dualize the whole definition, okay? So how do we do that? So let's just sketch it. So we have M set, okay? So now here we had multiplication. Now we have co-multiplication. So this means and the co-multiplication goes from m to m cross m. And we have a co-unit, which is, well, this becomes meaningless because it's from m to the 1-point set, which there is nothing here. And then co-associativity and co-unitality. So co-associativity, co-unitality. Yeah, but you can write down a full definition of this dual concept. We will come back to this. So just point out that we have it. Okay, so I want to put things a little in perspective by stating something quite beautiful from classical category theory. So microcosm principle. So this is due to John Baez in first stated and Jim Dolan in the paper in 1997, which is higher dimensional algebra, like third. So this is an influential series of papers. This happens to be the third one. And let me just state it. So they stated that certain algebraic structures can be defined in a category equipped with a categorified version of the same structure. Okay, so what does this have to do with? Well, this has everything to do with everything we will do today. I thought it's important to mention. Okay, so our example of interest, say, so let's translate this in our setting, right? So what does this mean? So let's take the certain algebraic structures part. Okay, in our particular case of interest, this is monoids or comonoids, it doesn't matter, they are just dual. Okay, can be defined so what's a category equipped with a categorified version of the same structure? Okay. So what's a categorified version of a monoid? It's a monoidal category, right? So this translates into saying monoids can be defined in any monoidal category. So I know this is like a too much philosophical discussion just to make this statement, but we must realize the theoretic underpinning of what's happening and how come the theory we see, I don't know, categorical quantum mechanics came to be in the first place. Now, in some sense, this states that like the appropriate place to study monoids and comonoids, whatever, is actually a category with a categorified version of the same structure, which is precisely monoidal category. Just wanted to point out, it's not a coincidence that, oh, let's just do these monoidal categories, etc. Okay, there are deeper principles which sort of make this work. Okay. Okay, so now let's just define monoids and comonoids in any monoidal category. Okay, so definition. So let C tensor I be, so this is, say, monoidal category. So a monoid in C is an object A equipped with so here we go. Okay, now it has a multiplication. So which we write, so let's just say multiplication in A tensor A to A. And we are interested in the graphical interpretation, so A tensor A to A goes like this. So right, and a unit, I would say element, but let's just say unit I to A, let's call this, I don't know, beta A. So we would just say this. So which satisfy, of course, just like in ordinary monoids, associativity and unitality. So the associativity, let's just draw a picture. So say I have 3 copies of A. So let's say I apply multiplication to the first 2. Let the third one be, and then multiply whatever is here. So these are both multiplications. So this is the same thing had I done the following. I multiply the other 2 copies, leave this alone, and multiply the other 2. Okay. Yeah, so this is associativity and unitality. Well, what's unitality? Okay, so if I multiply by 1, I get what I get. So, okay, how do we put this? So let's say I have my copy of A, and I multiply by 1. Right? So this is like empty space here. So, and this is A. This is a map from A to A. So just means that I recover the identity. And if I had, and the other way around. So if I take the identity and multiply by, so apply the multiplication, it's as if I did nothing. Okay, so this is how you define a monoid in any monoidal category. Okay, and again, the reason I took this sort of detour to get to this definition instead of just stating it and telling you to deal with it is that there is a sense in which monoidal categories are the appropriate place to define what a monoid is. And this principle appears time and again in all sorts of scenarios. Yeah, but we are interested today in this stuff. So let's just very quickly just examples. Okay, so first of all, so in the monoidal category of sets with the Cartesian product, so we recover what I just erased here. So ordinary monoids. Okay, so example which might be relevant for later, but today I don't think we will use this. So anyway, so in a field for all h, there is a monoid. Of course, I'm doing f hilb with the tensor product and the complex numbers as the unit. So we have a monoid and h whose elements are endomorphisms. I mean, linear functionals from h to h multiplied by composition. So whose elements are endomorphisms h to h and multiplication is composition. These are just to say something. I mean, I guess if you take this Cn with a choice of basis, say the standard basis, you get the monoid of matrices with multiplication, right? But except now you have to say that matrix multiplication is sort of compatible with the tensor, which means bilinear, and you can check these things. Yeah, that's what this is saying. Okay. Let's see if something good. Okay. So before I erase the principle there, so let's use this again. If I tell you now, where do commutative monoids make sense? Okay. So our algebraic structure is commutative monoid, and we have to define it in a category with a categorified version of it. Categorified version of commutative monoid means symmetric monoidal category. So if I want to define commutativity, I have to do it for symmetric monoidal category. So I guess this continues definition. Okay. Definition. So C tensor I, symmetric, let's say symmetric monoidal category, a monoid A, so according to that definition, is said to be commutative if, so let's just do the diagram. Okay, so I want to say something, right? I want to basically say something of the form x times y is equal to y times x. This is the meaning of commutativity. So I could sort of think of the multiplication here and then permute the input and the output. So if I am commutative, it means that this is the same thing as just multiplying. Nothing changes. Okay? You can figure out the relevant diagrams. They are not difficult to write. Just, yeah, one of the points was using these string diagrams. So let's just do that. Okay. Good. Okay, now let's jump further in the context of quantum theory. Okay. Oh, how am I with time? Sorry. I have 25 minutes. Oh, sorry. Give me a heart attack. I can't even state a theorem right now, let alone. Yes. I mean, it's a principle, like it's a meta-mathematical statement. It's not a theorem what I wrote, right? So it's just an observed pattern. Many algebraic structures. Sure. I mean, yes. Like you define what's like a categorified group, you come up with the definition of that, and then you say the definition of a group could make sense in that setting. Or
in that case, it breaks down. Find a group object in a category, you really only need
yeah, but the
it doesn't have to be groupable.
yes, good, but okay, so there you have, okay, for the since we started this, so for the group you have to observe that the inverse doesn't really play a big role in the, I mean, it's just sort of super added thing, so they still make sense. And yeah. Sure, you define a category with two monoidal operations which are compatible. And then you define a ring object in that category. I mean, it's just, yeah. Yeah, I mean, it's one of the gems of higher category theory, sort of observing these type of things, which brought things like this to fruition, in my opinion. So yeah. Okay, any other things? Okay, so we say dual things are sort of the same thing, but yeah, but dual things can be very different from the original. Anyway, so in the context of our particular quantum stuff, the more interesting notion is that of a comonoid. Okay. So let's briefly talk. Comonoid, fine. Now comonoid is more interesting for us. So let's just quickly write the definition of a comonoid. So again, same setting. We have a monoidal structure, monoidal category. So the comonoid let's again call it A in C consists of. So now let me just do this in pictures. So I will have a comultiplication. So okay, let me just write it. So comultiplication goes from A to A tensor A because it's the dual. So let's call this CA. And the way we would write it is like this. So I'm using the sort of circle unfilled to distinguish it from monoids. So we have this comultiplication. Okay. And we have a counit, which in this case is from A to I. And let's call it EA. So how do we depict this? Well, it's from A to I. So I have A, I map into I, which I draw as nothing. And this is the operation EA. So this is already now very interesting for information theory.
Sorry, I guess Vicary
yeah, I think it was bad.
That's
Yeah.
the epsilon, right?
They called this D Vicary Heunen. But I mean, I'm taking their definitions, slightly changing the, because I don't see why you would call comultiplication D. Yeah, I mean, there is a reason which we'll come to, but yeah, anyway. Okay. So yeah, so we have these two pieces of data, and this is already interesting for us because one way to interpret this is to say that comultiplication models copy. So if you just look at it pictorially, what you do is you have a copy of A, you sort of branch out into two copies of A, right? And then what does this model? You have A, and well, you destroy. So this is called deletion or destruction. Destruction, I think, is too epic. So we will call it deletion. I guess if we follow the quantum theory terminology style, we would call it destruction and teleportation and things. They have all this like Fanta. Okay, so all of a sudden, from all this like abstract, like very sort of classical structures here, we see something interesting. Because now we could make sense of the axioms. So these satisfy so let's write down what co-associativity means for the co-multiplication. Okay, it means that if I have A and sort of so let's think in terms of copying, right? So let's say I make a copy and I make a copy of one of the copies. And this I leave alone. So what is this process like? Making 3 copies. So this is the same as I have A, I do my copy, right? And I do a copy of the other one, and this I leave alone. So you can make sense of this co-associativity axiom purely in terms of, well, you're copying things, so, right? Okay, and the co-unitality, what does it mean? So again, I have A, and let's say I make a copy, and I have 2 A's. And let's say I delete one of them. So what I'm left with, so if I make a copy and delete one of them, is the same thing as doing nothing in the first place to A, right? And similarly, if I make a copy and delete the other one, is the same thing again as if I had done nothing. Okay, so we see sort of both the pictorial interpretation of co-multiplication and co-unitality and the axioms for co-associativity and co-unitality sort of actually model what it means to copy and delete, pretty much. Like, this is what we would have wanted from a copy and delete operation, right? So good, now we will use this. So let's do okay, great. So let's first consider some examples. So example 1, in any Cartesian monoidal structure, monoidal category. So by Cartesian, I mean that I have a category and the monoidal product is the actual categorical product. And so this is categorical product. And by necessity, this will be the terminal object. So here, any object A and C has the structure of a comonoid. So how? Well, the map, so this is the categorical product, which means, well, let's say what is so this is the diagonal, I guess. Okay, let me just denote it D to respect Vicary Heunen. So this is the diagonal map. Okay, so recall that by the universal property, a map into the product is the same thing as a map to each component of the product. And so we have a map from A to A, which is identity, and the map from A to A, which is the identity. So I just literally, I mean, you see also the copying idea here. I just make a copy. So I have identity, identity. And of course, in co-unit, here I have no choice because this is the terminal object. It is unique, and I have no choice. And so you can check that these axioms are satisfied. Okay, this is a general example. So in particular, what does this look like for sets? Well, the diagonal map from A to A cross A is simply the map which maps an element A to the pair A. So in the category of sets, we always have sort of a copy machine, let's say, right? We can always replicate elements like this. And the unit, well, the co-unit, I mean, just nothing.
It might be worth mentioning here that it's not just you always have it, it's that so these things that
I will state, if I have time in the end, I will state a theorem which exactly says what you're saying. So it's unique in the sense, okay, yeah, very good. Yeah, I think I will state a theorem which says what you're saying. So, yeah. Okay, so with the same data, you can do this in REL. So if you consider any set, okay, this is not the terminal object anymore, and this is not a Cartesian. So let's point out, right, as a note here. This is not Cartesian. I know we do the same product, but for instance, the one element set is not the terminal object in REL. The empty set is the terminal object. So this cannot be Cartesian. Yeah. Right. So still, like this same data here, so same data, because it will satisfy these laws. So yeah. Same data makes every object a comonoid, or provides every object with the structure of a comonoid. Good. Now, third example. So in F-Hilb, so let's say we pick some Hilbert space. So we can choose a basis some vectors ei, and once we choose a basis, then we can sort of in this manner impose a comonoid structure on H. So then we define the comultiplication to just map basis elements to your copying. Okay, and we define the, so this is multiplication. Let's call this, okay, let's call this CH. And the counit, well, I define it to take basis elements to 1. Okay, so this data, so then with this data, H is a comonoid. So these are examples from our categories of interest. Good. Okay, so okay, maybe let's leave this here just for this other example. Okay, so let's do another definition. So again, P tensor I, monoidal category, and let's say A, B are two comonoids in C. So a comonoid homomorphism is a morphism f A to B in C, which respects the comonoid structures. Okay, so I mean, if you're familiar with some stuff from algebra, like when you say group homomorphism or monoid homomorphism or anything homomorphism, it's a structure preserving map. So in our setting, it means that it will take co-multiplication to co-multiplication. So let's think about what this is supposed to look like. Okay, so first of all, our f is like something like this, right? From A to B. So we can think about it as like we have some A which has some information of interest. We apply, I don't know, maybe we do an experiment or something, F, and B is what we get, right? Okay, so this is homomorphic if we do this. So if I had A and I perform F, I get B, and then say I made a copy of B. This would be the same as taking A, making a copy, and then performing F to both copies. So in algebraic terms, we would say, so one interpretation of this is that we would say F preserves co-multiplication. Okay, and the other thing is that it preserves units. So This is one axiom. The other axiom is to say, if you have A, you perform F, get B, and delete. So this is the same thing as, well, you could have deleted from the beginning. Why perform F in the first place? So here we would say F preserves counits. Okay? Now, what I think is very important here is the following. So again, if you think in terms of what we are trying to model, etc. So if you think that there is some sort of process going on here, and this is an experiment you are performing, okay? So you perform experiment F, and from A you get B. And then you make a copy of the data that you get out of the experiment. This is equal to first as doing the experiment twice, basically. So what does this tell you? That this experiment F is very deterministic. If you do it twice, it's sort of the input A kind of determines the output B. You don't have variation, right? I mean, if you think about it from the, I don't know, in a physicsy way, quoting Salman, if you think in physicsy terms, this shouldn't happen, right? You do an experiment, you get B, copy the data. Why should I get the same B when I do the experiment twice? Okay? So the way, I mean, how I would interpret it, so F being a homomorphism, models F having deterministic behavior. So this is what we model by homomorphisms, right? So deterministic things. And okay, so let's observe this is actually case. Let me check for time. Not bad. Okay, so in examples, so let's proceed with the same order as there. So let's go to 1 prime immediately. So in sets, I mean, any function is deterministic. So if I have a function between sets, is a homomorphism for all f. Every function is a homomorphism. So how can we check that? Well, this takes an element A to something f of A. You do 2 copies of f of A. And this takes an element A, does a copy of A, then does f of A and f of A. Nothing to, And so this tells us that functions are deterministic. Which is a notion that came up in our lecture about dagger categories, if you remember. So we said the category of sets doesn't have daggers. And even then, having a dagger structure was sort of, I interpreted it as having a notion of non-determinism in the category. And here we go again. It appears every function induces comonoid homomorphism, meaning it's sort of deterministic because it sends elements to elements and you don't have a choice. Okay. So, okay, so let me say Vicary Heunen don't mention what I labeled as 2 there, and don't mention the fact that I'm about to mention now at all, but I thought it's sort of indicative of the nature of these things to point this out. So now in rel, okay, let me state it as a, I don't know, I don't want to say theorem, but okay, let's say proposition or fact or whatever. So R from A to B, so let's say relation, which means in the category rel, is a comonoid homomorphism if and only if R is a function. And so let me just prove it schematically. This is easy, you can do it at home. Okay, so proof. Okay, so assume R is a homomorphism. I mean, with respect to the monoidal comonoid structures here, with the diagonal maps and everything. So this would mean that these things are equal. So in particular, we have a commutative diagram like this. So I have I, so this is the diagonal, which is my copy. E here. So this commutes now, sorry. So this is R, and this is like R cross R, and this is diagonal of B. So this commutes. Now assume R is not a function. So assume A B1 and A B2 is in R. Okay, so what happens is the following. So let me just draw a picture. So I have my element A, and it's sort of related by R to both B1 and B2. And now I do a copy. And now I copy also these. Sorry, B1, B1, B2, B2. And in R cross R, I know that I have these relations by definition. But in R cross R, I also have that the element AA is related to B1, B2 because both AB1 and AB2 are in the relation. So when you take the product, this is also in R and also B2, B1. So we see that that square cannot commute, right? Because so if you compose, so let me use the red. So if you compose this way through the B1 and B2, you only get that A is sort of as an arrow to B1, B1 and B2, B2. But if you compose this way, right, if you compose this way, you get a connection to all four of these. So this just can't happen. So each A has to be related to a single thing. You can also show, like, you cannot have A empty, things like that. Okay? But this is true. Okay, so, and the reason I showed the proof is because it's not in the book. Otherwise, it would have been an exercise. Good. Now in 3, so let's say we have H, K comonoids in F Hilb, which means for both of them I have chosen a basis and they structure maps. So this you can go check. So F H to K is a homomorphism. Just in case, F of EI is a basis element of K for all EI in the basis of H. Okay. So this is a very weird notion from the point of view of linear algebra. Okay, we never see such type of maps or this concept altogether. Okay, it's only when you, I mean, there is an interesting connection between these two examples, which I'm not going to go into, but it's very interesting that this sort of happens, and I'm not sure why Vicary Heunen sort of failed to mention this, or I misread the book, I'm not sure. But yeah, there's this thing. No, it's not. It's a linear map which maps basis elements to basis elements. So things go in straight angles, if you wish. Like you either collapse 2 dimensions into one, or you just leave it as is. So that's the notion of sort of being deterministic. Right? So when I say that H and K are comonoids, I mean that I have already chosen a basis for both of them. Okay, they come with a chosen basis. No, it means that it's a basis element for each basis element. It just takes basis elements to basis. I mean, if you think, I don't know, R2 to R3, things like that, the basis vectors have to go to basis vectors. So you either can collapse like a plane to a line, or you leave the plane as it is. There's no other things you can do with this type of. It's sort of interesting that this sort of very high rigidity, right, is the notion of deterministic for this type of linear maps, right? And that's what it would be, deterministic. And here, yeah, just think it's interesting. Okay, so I'm a little short on time. I'm sorry. Okay, so oh, by the way, before I erase, this idea that was written here, like being a morphism which preserves these. So in the field of categorical probability theory, this is taken as the definition of something being deterministic. So, I mean, it's not like I came up with this interpretation or anything like that, okay? It's just a theme that appears elsewhere, that's what I'm saying. Okay, I'm gonna erase. So, okay, now we want to talk about, so we will model another concept today, okay? And let's get to the point. So natural, so this is section 3 of this lecture, I guess. So natural slash uniform. So copying and deleting. Okay, so this is the term used by Vicary Heunen, which I don't like. I mean, we have a term in category theory called natural. Why use the term uniform? Doesn't matter, it's just terminology. It kind of makes sense as well, but anyway. So let's just write what this is and we'll explain. So let's start with deleting. Okay, so definition. So C tensor I, as always, monoidal category. We say that it has natural deleting if for each object, well, in C, we have a map, a morphism, EA from 8I such that well, okay, so sorry, let me slightly, just for emphasis, So we have a, so this is what we call natural. So in category theory, you will hear like a natural is a natural isomorphism, natural. So Walker has been added all the time. And I'll explain what it means, but it just means a natural morphism like this for every object, such that if I choose I here, this is the identity. So what does natural mean? Oh, let's put marks here. Okay, so what does natural mean? So let's explain it here. So natural mean that also the reason for the term uniform means that this choice of morphism from A to I, we do it in some sort of systematic manner, which means that given f A to B, we have this commutes, which just means that whatever EB EA. So this is the categorical meaning of doing something naturally or uniformly on all objects. Okay. So it's just if you have done, I don't know what classes you might have taken in math, but when we do a mathematical construction, so let's say, I don't know, given a topological space, you construct the fundamental group, for instance, right? And you do it systematically in a way which is sort of for all spaces, things like this. So this is notion of functoriality, naturality, cover this idea of doing things uniformly and systematically for everything. Okay? Okay, so let's also draw yeah, I mean in string terms, what does this say? I have a I have, I don't know, FA to B. So this is my F, and then I sort of delete is the same thing as deleting. And this is true for all F. And now, fine. So the interpretation we have of this so this models like let's say a machine which carries out deletion in a systematic manner. So this is our concept of interest. Okay, so we can say like a deletion machine is a choice of deletion operation for each object, which is natural, meaning you always have this thing here. And now yeah, so there are theorems. There's a theorem called no deleting, which let's get to that. So first of all, okay, so a little proposition. So, I mean, okay, whatever. Sorry. So, if C tensor I has uniform deletion, then yeah, I is the terminal object. Object, so equivalently, so we say in these cases, C tensor I is semi-Cartesian. Yes, do we say that, Volker? Okay. So if you, okay, this example is still here, which is good. So Cartesian, monoidal structure is Cartesian if the categorical product is the monoidal product, and in which case the terminal object is the unit. But unit being terminal doesn't mean that the monoidal product has to be the categorical product. Just saying. Okay, so that's Cartesian. What's spilled out over there, this is semi-Cartesian. Okay, good. Now, do we prove this? Let's see. I mean, since it is easy, let's prove it. Okay. I mean, one direction. So let's do this direction. I think is the, so if I is terminal, okay. So I mean, terminal object, there is a unique choice for a deletion operation by saying that I is terminal. Terminal means there is a unique map to it. So we do have this unique choice. And I mean, and the naturality, well, you have any map here, you compose it with the map from B to the terminal object, it gives you a map from A to I. Given that there is a unique map from A to I, it has to be EA. Yeah. Yeah, this. Yes. Sorry, let me double check. I mean, are you sure that's not for the? So sorry, you were saying that in the book, what they call, there is compatibility with the tensor structure. Sorry, apologize. Yeah, I'm sorry then. What? Okay, I guess I just made a new. Sorry, I made up. I apologize. Uh, I mean, this requires compatibility with the. But they have a. Oh no, this is from another chapter. So we are reading chapter 4. Cihan, not this.
Okay, so that they call this also
Uh, yeah, okay, so I couldn't be that blind last night when I prepared the talk. So
Yeah, that's why I was
no, in chapter 4, yeah. Now, because this is interesting, like the only difference, I mean, the only condition besides naturality that appears in the definition of uniformity is that this is true. And this is for, actually, I mean, yeah, I mean, you can define this for any category, well, no, monoidal category, but whatever. Like, if you look at chapter 4, it needs, because no, this I has to be the what?
No, what I'm saying is this definition
Mm-hmm.
does not involve the tensor.
No, no, this has to be the unit of the monoidal structure where you delete.
Right. What I'm saying is you can make this definition.
I mean, you choose a category with a chosen object. Yeah, okay. Yes. Yes, but that's how they do this in chapter 4. Yeah. And then that is true. I mean, okay. And then, yeah, sure. So Walker is saying tensor product doesn't come into play here, and it doesn't come into play here because this is a statement about I. So, yes.
I mean, I don't know if they can be equal.
No, you don't, like, like the proof is just, okay, if I is terminal, we have this uniform deleting, and if we had the uniform deleting, then this is terminal, because, okay, so assume we have an object A, and I have like 2 maps to I. So we have uniform deletion, and then assume you have another, well, let's call this G. So then we have the identity of A here. By naturality, any map commutes with the structure. I mean, no. So I want to prove there is a unique map from A. I want to show that this G is actual. No, sorry. Assume I have the G here, and yes. So let this be EI, which is identity on I. So this axiom is important. And sorry, you have to erase again. Let this be another F, as here, it has to commute with the deletion maps by naturality. But since we chose the deletion map for I to be the identity by assumption, then it follows that EA is equal to F. Okay? And so I is the terminal object. There can't be 2 different maps from A to I. Okay? And now, let me check for time because I don't know what I have time to do or not. Okay, let me just state a couple of theorems. The proofs, they are very transparent in the book. In terms of string diagrams, you can unpack them. Now, in some sense, this is a no-deleting theorem in itself, right? So what does it, okay, Selman was mentioning in physics, in quantum physics, so these no-go theorems, that's how they would say. The no-go theorem is you can't do something, okay? So this is telling us that if you could have this uniform deletion in the monoidal structure, the unit has to be the terminal object. Okay, so we already, for instance, looking here, so this tells us that we cannot build a uniform deleting machine here, because C is not the terminal object. Nor can we do it here, because the terminal object here is the empty set, right? So this is already like a no-go, okay? So let's point that out. I mean, they could have called it this no deletion theorem, okay? So this is a no-go theorem for deletion. So what they call no deletion theorem is something more complicated, but I will just write it down very quick. So so they call this no deleting. Okay, so C has, well, C tensor I, uniform deleting, if and only if the set of morphisms CAB, so there is a unique morphism between any two objects for all A, B, and C. We call these categories, and also the book, this is called a preorder.
So you have to be using uniform
Why?
because there are semi-Cartesian structures that are not preorders. So in this proof, you've shown.
Then this is a yeah.
But if it's terminal, if it's say Cartesian, we've already seen.
If it's Cartesian, it is uniform. You have uniform deleting.
Right.
Oh yeah, this is okay. So this was.
Because the reason there contradicts.
Yeah, this is an if and only if. Sorry, I didn't get it. Like
So
you have semi-Cartesian structures.
Set has uniform deletion. Let's
Yes.
just stick with that. It is not a preorder. So you have to be using uniform deletion.
I think I might have. I mean, is set compact close all of that because they have some assumptions.
I mean, I think that here it's probably compatibility with the monoidal structure.
But this is the theorem from chapter 4, the one they call no deleting. I mean,
Chapter 4. I could only find one.
I mean, in the syllabus, this was the reference. Yeah, could you find it quickly? I'm curious.
No,
Like,
I couldn't find it in chapter 4. I would only find anything about.
Am I using it?
in chapter 6? So.
About deletion? No,
Yeah, but I was
right here. Where they
I haven't made it.
4.2.
yes.
No, this is the different.
Oh,
So I'm using whatever Salman has.
He's using the one from is it Oxford Press or whatever, the one online that I sent.
Yeah, yeah.
Not the lecture notes.
So yeah, we have to correct this theorem because Walker is right. Could you quickly look it up?
Okay, the compact category has
Compact, yeah.
Let me just double check.
But isn't set compact?
Yes. No, so
Deleting uniform deleting.
Yes. Definition of uniform deleting is correct.
you need all duals for the definition.
Okay, so C, okay, exactly. So compact. So I said C monoidal category because I was lazy to write it, and it gave us problems. So compact monoid. So compact means all jewels. Set doesn't have all jewels. Just to distinguish. Okay, but thank you for pointing that out, because what I wrote here was totally wrong. Okay. Well, as I said, this theorem for me is more of a no-go theorem than this, because I mean, this tells you what happens to the category, how the structure collapses from uniform deleting is an interesting statement. But this is more of a quick check, right? Like you have a category, if your unit is not the terminal object, you cannot do uniform deletion, which is, I think, kind of a fantastic thing to conclude just from looking at the unit of a monoidal structure. So how many minutes do I have exactly now? 2. Okay. So what do I want to say? Okay, yeah. I mean, there's nothing to say in 2 minutes. So I apologize for not managing time as I wanted to. I wanted to at least state the no cloning. I mean, at this point, I think we have given enough explanations of what we are modeling, etc. I mean, you could really say for yourself, what does it mean that we can't clone? So can we have a copy machine which does this systematically for all A? What does it mean to do this systematically? Well, there is naturality like here, compatibility with the tensor product, and things like that. Okay, doing this naturally means that if I do any experiment, it's the same as, well, sorry, sorry. Yeah. So this is one of the conditions in natural or uniform copying. It has to be like this. We saw how restricted these things are, right? I mean, and there is a theorem which is similar to this. It tells you that something drastic has to happen to a category to have uniform copying. Something very drastic. It's actually interesting. It means that if a category exhibits cloning, then sort of any f between A to A is of the form identity A times trace of f, in the sense that Walker explained. I mean, basically any endomorphism collapses into this scalar multiple of identity form. Just like here, you see every morphism set has to collapse down to a point. So these are the no-go type of theorems. And of course, this being true, I mean, it's not true in any of these. And then another interesting theorem, last sentence I will say, so being a Cartesian monoidal structure, I'll just write it down as a note here. So there is a proposition which says that being there a Cartesian monoidal structure is the same thing as having uniform copy and delete operations. So having both uniform copy and delete operations is such a strong statement that only in the Cartesian closed, yeah. And yeah, remember there is this compact assumption here. These are not really, but I mean, it's such a strong thing to ask that if you introduce any slight idea of non-determinism in your category, this theorem tells you you cannot do that, cannot build these machines. So yeah, thanks for listening. I'm sorry for.
As to the terminological distinction, I think the reason that I didn't want to eat up more of your time is because if you were to write down a priori a definition of natural, this has an extra condition.
Yeah. But it's just the gist of it is doing things naturally. I mean, that's the actual part.
But I mean,
Yeah.
these propositions don't hold. So like,
I know.
C has natural deleting in the
I know.
sense,
Yeah.
or sorry, finite filtering spaces.
Yeah, I guess I
You
over.
can factor the map to C
Yeah,
through the zero vector
I guess I
space.
overreacted to this being. Yeah, my I got triggered as a category theorist, but no. So no. Okay, so
He wants to emphasize that these maps E should form a natural
yeah,
transformation. And
but
that's
there is
one of
this
the two
also.
conditions in what
Oh, so that's
Okay, so this is definition of uniform. Okay. So you ask this to be a natural transformation, but you also have this condition.
that's uniform.
Yes.
Okay.
I said natural
Well, I thought it was
deleting.
here too.
Yeah.
Yes, I got it right.
Yeah. Yeah. I mean, I just thought, I don't know, emphasizing naturality is sort of, yeah. Yes.
For the barbarians amongst us, pre-order, can you remind me?
it is this condition.
This condition, if you have a unique element in every home set, I mean, it's a pre-order because basically it tells you, is there a morphism or not? That's the only information you have, which you can interpret like this.
I mean, it's slightly miswritten now that I realize it. It should be is either the singleton or the
Yes. Okay, at this point you can see I'm too tired, so and I couldn't, like, to me labeling one specific theorem as no deleting is not the appropriate thing to do. This is also a no deleting theorem. I mean, when I read this theorem, I was already satisfied, so this I just noted out as a curiosity more than anything. Yeah.
Sorry, is semi-Cartesian category the same as what Heunen and Vicary calls Redi monoidal category?
No, braided has to do with the symmetries.
So
Semi-Cartesian, just the unit object is the terminal object. That's it.
braided is a weakening of symmetry, whereby these twists that you get. So remember, we have these interchange rules for objects in a symmetry. A tensor B tensor C is the same thing as B tensor A tensor C. Those form up to isomorphism, up to chosen coherent natural action groups, the symmetric groups in the symmetric monoidal category. In a braided monoidal category, they form representations.
So there is something interesting also, like in categorical probability theory, when you look at the definition of Markov category, they ask for the monoidal structures there to be semi-Cartesian to begin with, which means you can sort of do this trick here and have this natural copy thing, which is there in the structure there as well. But yeah, anyway.
There are several no-cloning theorems, let's say, because
Yeah, I mean, this is, you can consider this to be a no, I mean, a no-go. So I like the physics term no-go theorem. So no-go theorem is this happens, this drastic reduction of structure has to happen if you have these machines. And in some sense, this is also a very drastic thing to happen. Like the monoidal structure has to be Cartesian if you have natural copy and delete. So if you have non-Cartesian things, well, you cannot have both copy and delete, for instance, things like that. All of these theorems are of this sort.
So is this what you were saying when I was asking about uniqueness?
Yeah.
So the uniqueness that I meant is in a Cartesian monoidal structure, comonoid structures are unique.
I guess that's true. Yes,
Yeah.
because
Yes,
because they are, yeah.
The unit axiom says that
Yes,
projection
yes,
can
yes,
be
yes,
identities,
yes.
which
Okay.
determines
Yeah, then I haven't understood, but okay,
the
yeah.
because that's, to my mind, that's like the big difference between comonoids in set and comonoids in F-hill. You can choose a comonoid structure in F-hill,
Right.
but you can't in set.
I mean, yeah. Okay. Yeah, sure.
There might be a difference of versions. Like all these interpretations that we are doing, I'm not sure correct are they? One's correct. Like for example, naturally deleting. How right is it to say that like, deleting has to be like this? I mean, I can see the naturality in terms of
I mean,
mechanics,
it's
but I mean, physics might not.
okay.
care about
I
that.
would say is as correct as saying that the distance between you and me is a real number. Why? It's an assumption. So I mean, assuming that copying and deleting behaves like that, like you make a copy and then another copy is the same thing as making a copy and then like having.
Are you familiar with the normal no-cloning theorem in quantum mechanics?
Cihan, is this
Okay,
yours?
then it will make more sense. So the idea is that you have a quantum state, which is a vector in some Hilbert space, and for any given vector, you want to find if there's a unitary that makes a copy of that one for any given vector. Now, there is no such unitary for any given vector. Of course, it's the case that if you know a particular vector, you know exactly how to prepare it. That is, start from some zero and apply unitary to get that one. And then you can, of course, you're picking out a basis. Then, of course, you can do that on both tensor copies.
And this for any in there is actually literally naturality.
Yeah,
exactly.
That machine.
Yeah.
If you interpret this in finite dimensional Hilbert spaces, it's literally exactly.
Yeah. Yeah.
So
So
makes more sense.
that's where the naturality it's very much almost exactly or exactly on the nose.
Yeah, but I'm saying the moment you say there is a machine that's doing something, like let's say there is a machine that cuts heads off of human beings. Oh, sorry. So it needs to know what a head is for everyone, and yeah, same. You need to sort of input into it some general notions in a systematic way, right? While if you need, okay, okay, what? Yeah. I don't know why like I grew up on Eminem, so the first thing that comes to my mind is like cutting someone's head. But yeah, okay.
Keep that as bloopers for
The inevitable BilQC quantum seminar blooper reel.
Okay. Okay. So, thanks everyone.